Hi, people. Welcome back. And I tell you what, this is like my 6th time starting this. But I'm hoping this time is going to be the right one. So anyway, we've gotten our introductory look at vectors and scalars. All right. Part of that, well, the differences in those two are going to play a big role in what we talk about on this slide and in some of the relationships we start to develop in the next couple. Okay, so in general, in this unit, we're talking about what we call one-dimensional motion. And one-dimensional motion, one-dimensional part means in a straight line. Okay, things that move in straight lines, like I roll a marble across the floor, moves in a straight line, assuming the floor is level. We drop a ball, right? That thing moves in a straight line downward. We have these battery-powered cars that move in straight lines when we turn them on, and so on and so forth. All right, let's talk about some characteristics about the objects, objects' motion that we can use to describe it. Okay, so for sure, it'll be important for us to talk about. I'll start with. It seems simple. It's not so much about them moving, but if we talk about where an object is located, call that position. All right, so I'll say, I'll call that object's location relative to an origin. And by origin, I don't mean anything with graphs and axes and all that. Origin just means a place that we call the origin. So where are we relative to that? Well, we can measure how far away you are from that origin in meters. And we call position X, like X marks the spot. There you are. Okay. We can also talk about, let's say, how far object travels. All right, and we're going to call that distance. We can measure that in meters, and we'll call that d. Now, you might remember from our discussion of vectors and scalars that sometimes we talk about how far things go, total distance traveled, but sometimes we talk about, well, how far they've gone and in what direction from where they started. And we call that, if you remember, displacement. And we can measure that in meters also. But that deals with not necessarily how far you've gone, but how far you end up away from the origin. Or really, we call it change in position. And I guess I shouldn't say how far you end up from the origin, really how far you end up from your initial position. All right, so that involves something about, well, there it is, our change in position. That means we're comparing a final position and an initial position. And an initial position, yeah. All right, now the change in thing, you'll see that a lot, delta. We use delta to mean change in. And position, right, from up here, is x. So displacement, we call delta x. Now, distance is a scalar. Displacement is a vector, so a lot of times I'll do that. Position also is a vector. I'll do that little vector symbol to mean it's a vector. All right? Two other big quantities we can use to talk about objects' motion. We can talk about how fast things go, speed. And we'll use, well, I guess an S for that. And we'll measure it in meters per second. And that's how fast object travels. But you might also remember there's that fancier way to talk about, well, something a little fancier than speed. We call that velocity. That we'll do with a v. I'll say it's a vector. We also measure it in meters per second. And, well, for now I'm going to say this. how fast object moves and in what direction. Right? Up here, notice if we want, we could also say that, well, displacement is kind of like distance, so we could say how far you go and in what direction. But this is the better total definition of displacement. There's actually a better total definition of velocity. We're going to get to that in the next page. Now, the one thing we don't have on here, and I need another row in my table, but we'll just add it on the bottom, is notice we've identified that. Something about time, how long things take. All right, so I'm going to add time in the bottom. T, measured in seconds, and we'll call that duration of travel. Fair enough? Now, there will be more. One more big one, but also we're going to really have to sort of focus into some clarification of really two of these to be a little more specific about what we mean, but that's okay. We'll get there. So far, so good? Okay. Let's look at, let's try to do some clarification between two of these that seem like they're very similar, but there's some big differences. All right? And to illustrate it, we'll use this case here where we say, here's something that has a certain starting position and a certain final or ending position. All right, now first of all, notice some notation. Position, right, we use X. Right. Position, we use X. Now this little 0 is not really a 0 after it. It's called a naught. X naught. The naught means initial or starting. And there's X for final position. Notice we don't use any subscript at all after the variable. That means final. So we have X naught for initial position and X for final position. Okay? So let's say that somebody walks this way and walks that way and walks this way. And let's quantify this a little bit. And let's say that this person goes, oh, I don't know, 12 meters east. And let's say 4 meters south. And this must be 12 meters west. Well, what's the distance traveled by this person? The total distance traveled is, well, 12 and 12 and 4 is 28 meters. Remember, distance is a scalar. There's nothing that we have to include about direction because distance doesn't have a direction. A person has traveled 28 meters. They have walked that far. All right? We literally add up the magnitudes of those vectors, the length of those vectors. Yes? Now, let's say to know how the speed that this object had, well, on average at least, I'm going to say, I'm going to put that big bar over it to mean average. And to find speed, oh yeah, well, we said this is how fast. In this case, I'll put in parentheses on average. You get rid of this comma. How fast on average object travels. Oops. To find speed, we're going to do, and again, I'm going to do average speed is distance over time. So let's say that the total travel time is, oh, I don't know, 7 seconds. I picked crappy numbers. Oh well. So if I had said, oh, I got it. Yeah. Let's say this is 3. Let's say this is 3 meters. Notice what I'm changing. Let's make this 3 meters, and we'll make this 27. 27 meters of total distance. Fair enough? So distance over time, the distance traveled is 27 meters. And we're going to change this. We're going to change this to 9 seconds. In 9 seconds. Well, our average speed is 3 meters per second. Yes? Now notice, there's something else we can talk about other than the total distance traveled, right? We can talk about how does our final position, x, compared to our initial position, x naught. Well, the displacement here, if you can tell, is the resultant of these three vectors. Here's what we call delta x. So what's our total displacement? Or how does our final position compare to our initial position? Or how much has our position changed from beginning to end? Well, our total displacement is 3 meters south. Yeah? Now, here's where we get a better definition of velocity. By definition, velocity is the rate of change of position. Now, before we said how fast you go and in what direction. Well, yeah, that's sort of true. But this is the real technical definition. And it actually should lead us to an equation. All right? And so we can say that, again, I'm going to say average velocity. Notice in the slide before I just said velocity. All right? Here's where we clarify a little. What velocity are we talking about? We're talking about the average velocity over this whole travel. I got to clean that up. Well, the definition is the rate of change of position. Well, change of position is delta x, and rate for us is always going to mean per unit time. You got me? Rate means how fast things happen, how fast you change position. All right, so delta x per second, change of position per unit time. So for us, that's 3 meters, notice, south in 9 seconds. Or if we want to be exact, well, how about this? I'll say that's 0.33. Sorry about my sig fig fail. 0.33 meters per second. And don't forget, come on, we have to include the direction south. So notice, speed, velocity, do not have to have the same magnitude. Right? The magnitude is the number part. Okay? Gotta know it. Gotta know it too. You'll do that more. Gotta know it. Gotta know it. Fair enough? Good. Come on. Come on, come on. Yeah. Okay, let's do some simple ones. My boy Porcel, this is Josh Porcel, coaches with me on the lacrosse team. He shoots 15 meters from the goal. It takes 0.3 seconds before the ball is in the net. With what average speed does he shoot? Well, if we want average speed, we want a distance and a time. So we have 15 meters, time, 0.3 seconds. It looks like that's 50 meters per second. Is that right? Yeah. Fair enough? Yep, that's it. Now, a pass, the blue here, a pass might be thrown at an average velocity of 25 meters per second. How long does it take the ball to travel 15 meters? So here's what we do. We start with a formula. We do have a displacement. Now, it doesn't give us a direction, but that's okay because we don't always have to plug direction to this. We want to know how long does it take. So let's solve for t. So what I would do first is this, and then we get t is meters in 25 meters per second. So that's what, 3 out of 5, 0.6 meters, whoops, 0.6 seconds. Got to be able to do that algebra, folks. You'd be surprised how many people have a hard time solving for t there. Now, here's where they get a little bit trickier. An actual shot really slows down from, let's say, 40 to 38 meters per second as it travels. Why? First of all, why? Come back ready to tell me why tomorrow. 2, how far does this shot travel in that much time? Well, how far? We know a couple of velocities. We know a time, we want a how far. So we're going to start with the one equation we know that involves velocities and displacements and how fars and times. And we're looking for a delta x, v average times t. Notice, v average. What's the average velocity? Well, if it goes from 40 to 38, the average, you might be able to tell, is 39 meters per second, 0.65 seconds. So we can actually add this equation. I mean, this is nothing groundbreaking. Notice what I'm doing. Take 2 different velocities that you know, add them up, divide by 2. Right? Like, you want to know what your average test score is. Add up your test scores, divide by the number of scores. Okay? Tell me what that is when you get here tomorrow. But notice, here's the big deal, right? You can't use any old velocity you want. We have to use average velocity. You do this one for tomorrow. Yes? Okay, it's part of your homework. I'll check. Next page. A little harder. Jill drives 20 meters per second north for 10 seconds, then she slows down. Different speed for a different duration, then speeds up. Different speed again, different duration. What's her average velocity? Well, the tendency of a lot of people here is to say, okay, here's a velocity, and here's a velocity, and here's a velocity. I want the average. Well, add them up and divide by 3. It does not work that way, folks. It does not work that way. Okay? Because of this, different durations for each one. Okay, so here's what we have to do. We want to know average velocity. We want this, total and total. If we know the total displacement and the total time, we can find our answer. And here's what I'm going to do. I'm going to call this interval 1. Call this interval 2. And I'm going to call this interval 3. Let's find our average velocity. So in interval 1, here's what we can do. We can figure out how far she went. Because notice, we know how fast she went for what duration. So we can say for interval 1, we know how far she went. 20 meters per second. North. 10 seconds. 200 meters north. Yes? Interval 2. Delta x2. v2 average. v2. So 10 meters per second north. 40 seconds. And that's 400 meters north. Interval 3. 40 meters per second. Whoops, also north. Sorry about that. 20 seconds. That's 800 meters north. Uh-oh. Fine. Now, if we want her average velocity, okay, fine. Average velocity is delta x total, p total. How far total, or what's her total displacement? Well, notice, she went 200 meters north, then she went 400 meters north, then she went 800 meters north, for a total displacement of 1,400 meters north. It took her a total of 10 plus 40 plus 20, 70 seconds. We have an average velocity of 20 meters per second north. Yeah? It's okay? What about our average speed? Sorry. What about our average speed? Is it different? Well, speed is going to be distance over time. Oops, time. Distance traveled is, well, still 1,400 meters. And it still took, for sure, 70 seconds. So the average speed is also 20 meters per second. That's a 0. But no direction here. Speed is a scalar. Right? That says 20. Fair enough? Okay. You do this one. All right? And the big deal here, notice, east, west. The easts and wests have to figure into the problem. All right? Oh, yeah. I believe there's a question here also that says, what about speed and velocity here? Are they the same? Are they different? Make sure you answer that too. So we just follow right along with the model we used in the last page, but extend a little bit and figure out how we use east and west. If you have to make a little drawing, a little sketch, that might help. Feel free. A sketch of the displacement vectors. That'll help. Could help. Okay? So you've got a couple of things to do for homework, and I will see you when I see you. Bye, folks.